Welcome to the Osmo Dev call on SIM card profile generation, personalization, and production. So that's a very specific topic, but nevertheless, I think it's something that not many people have a lot of insight into. I also don't claim I have a lot of insight into it, but at least some. Yeah, before we start with that, a very quick flashback to a talk I gave at Osmo, not at Osmo, at this last CCC Congress in 2019. I really like that slide because it's it's a dotty graph of all the different SIM card specifications and their references to each other. Always find that quite enlightening to understand how convoluted this world is, this SIM card world. Basically, it includes the ISO, the ITU, ETSI, 3GPP, global platform, and a couple of other standards bodies. And all of this together then forms what SIM cards really are. I don't want to go into the details about the SIM card technologies too much here, but I will every so often jump to that old slide set to illustrate some bits and pieces. So yeah, so what is this about? Basically, it's about how SIM cards are made. On the one hand, physically, where I have no real first-hand knowledge, and then more on the logical side, on the software side, how they are made, where I do have insight into, because Sysmocom, my company, is well, not physically producing, but still creating SIM cards on a logical level and providing them to a number of customers. So SIM cards basics in this slide deck has fixed me. We can quickly go back to that other presentation. So I'll skip all the lower level bits. So we have on SIM cards, first and foremost, a file system on the card. File system not in the sense of a block device, like a USB drive or so, where your file system is implemented on the PC, but the file system is implemented on the card itself, in the processor on the card. And then you have a file level commands to open, read, write, and so on files on the SIM card. Some terminology here, master file, dedicated file, elementary file are how they call root, subdirectory, and data files. And in terms of data files, there are different structures of files. Transparent files is just a blob. Linear fixed files are record-oriented, and you can seek to individual records, and you have access control conditions, which are the permissions to those files, who authenticated, who through which channel authenticated by which means can access the cards in one way or another, or modify bits and pieces of it. And SIM cards are spoken to by commands. Some of the key commands, file system related or not, we can see here. So selects a file or directory. Then we have read and update commands. We have pin related commands, which interestingly, at least in some parts of the specs, are not called pin, but CHV, card holder verification, but it's just a synonym for the personal identification number, PIN. I think PIN is more in the bank sphere, and CHV is more in the telecom sphere. Then we have commands like run GSM algorithm, or in modern cards authenticate, to perform the authentication and key agreement implemented on the card, and so on. And this is a small snippet of the directory tree that we see. This is from the original 11.11 or 51.011 specification for old SIM cards that show you sort of how these directory trees look like, and the files and directories, or rather the EFs and MFs and DFs in this tree. In addition, we have so-called applications on cards. An application can be code, but also file system. One of the applications that we work a lot with is the USIM application, which is used for 3G, 4G, 5G authentication on the card. And with that, I think we can go back to the actual slide set of today. So, and let's first look at SIM card production. I don't have any pictures in my slides because I could not find any that have actual permissible reproduction or sharing rights. So I'm not sure if it helps me much, but I can just open a web browser and show you some stuff that's online on the web. So it's not a slide deck that I reproduce, but just like reproducing the web browser window of stuff that other people have published. Not sure if it helps in terms of copyright, but at least I can give it a try. So what kind of elements do we have in this card? We have the chip, of course, the system on a chip, you could call it, that we talk to. It contains the CPU core, RAM, flash memory, sometimes ROM, and at least the UART, which is the serial interface through which we are talking to the card. Speaking of UART, we can put a quick reminder to Sylvain's talk on an open hardware FPGA core smart card interface UART that was here just a few weeks ago, a month ago or so, in the Osmo Dev core. So you can check that out in the history. These days, ARM also has a pretty strong footprint in this domain for SIM cards. In the past, it used to be lots of obscure 8 and 16-bit microcontroller architectures that nobody has heard of outside of the chip card domain. But now we have a Cortex M0-like device called Secure Core SC000. There's also a Cortex M3 type, but I don't think you will find it in SIM cards because it's too expensive for most use cases. Those chips are, of course, manufactured on wafers like any other semiconductor devices, on silicon wafers, and then the silicon wafers are diced into dies. The next part that we have in SIM card physical side is the so-called microconnector. That's the actual industry term for the 6 or 8 contact surface area of a smart card. I guess everybody knows how it looks like, but I cannot. Oh yeah, shouldn't try that with the camera. How it looks like, if you search for this kind of picture, this is actually how these are like produced, on the way how they are produced. So you have a 35 millimeter reel that actually has been inspired by 35 millimeter film at the time, in I think the 70s, 80s, whenever they did that. So it's a 35 millimeter reel with like at that time a movie theater film roll reel, and these are produced in processes not unlike flex PCBs, these contact areas, and they're called microconnectors. So if we combine the chip with this microconnector, we end up with what's called a module. That's the basically combining all the electronic parts of the SIM card without the plastic yet. So we use the module, we use the microconnector, we use the chip die, and we have 3 steps. First, we have die bonding, where we fix the chip on this microconnector. Then we have wire bonding to connect those contacts on the microconnector with the die. And finally, encapsulation, where some resin, epoxy, whatever blob is put on top of the chip to protect it. And this looks, oh, there we are. This is the one that I wanted to show. So there are some pictures in this LinkedIn post. So we see here the wafer being probed. Here we see microconnectors in 2 different views. Here again, one of those 35 millimeter reels. And here we see the process of putting glue on the microconnector and then putting the die on it to bond it to the microconnector. Finally, we have these bond wires, like in other integrated chip packages, that connect the chip with the microconnector at the bottom here. And then in the end, we put some blob of epoxy or some resin here. In this case, it's a semi-transparent one. So you see the chip here, the bonding wires at the edge, and basically the backside of the microconnector. And this together all forms the module. And this module then meets at some point with the plastic card. So the actual plastic card of the SIM is produced independently. It's typically PVC or ABS. In terms of plastic, produced from foils in some reel-to-reel process, and then once you have the individual plastic cards, you print them typically, and then at the end there is a milling happening for the location where the module is to be mounted into the card. And in this milled space with some glue, there is the so-called module embedding, where the module, the electronic part, is glued into the plastic card, and at the end you have a physical smart card as we know it, as you purchase it basically. And that's for the physical side. So if we try to summarize that on one screen, we have this again here. We have the microconnector with the chip wafer that gets diced, and we have a chip die. Those two are combined in the module production, die bonding, wire bonding, encapsulation, and we have the plastic card that gets printed and milled. All of this goes through the so-called embedding, and in the end, we have the physical smart card. Okay, and are we done now yet? Well, yeah, we have a physical card, but the card doesn't really have any data on it. In the worst case, at this point, the microcontroller doesn't have software on it, so it still needs to be programmed in some way. And that is what we call the personalization process of the card. It gets its personality. Before that, it's just a controller that could do whatever. And now it gets personalized with software and data on the card. And that basically is what kind of software and data do we have on the card? Well, first of all, there's typically a bootloader. That bootloader is most cases a ROM-based bootloader. Sometimes can also be flash-based, depends a bit on the architecture. If you have multiple layers of loaders or so, then we have the card operating system itself. We have the file system hierarchy, where I just showed this small graph, including which files exist at all, what size do they have, what structure do they have, what content do the files have, and what access rules exist for those files. And last but not least, the applications, which can contain code and or another application-specific file system tree, the so-called ADF, the application dedicated file. And all of this now needs to be brought onto the card. And before we can bring it on the card, we of course have to create or specify or define that all in some way or another. Now, the card operating system, there are card operating system vendors out there for decades that produce operating system for smart cards. All of them that I know of are proprietary. There's no open source in this domain. There is some very small exceptions. If you think of, I think there's an OpenPGP smart card implementation that's open source out there, but beyond that, I'm not aware of any usable open source in this domain. The operating systems in the past, they used to be, assembly and very machine-specific C code. Today, they're often quite portable and support a number of different chips from different vendors. And this card operating system is licensed with a per chip royalty from the card operating system vendor. And also, if Java is to be supported with Java cardlets, then there's this royalty to Sun and Oracle. There's a question if there's something like OpenJDK for Sims Java applets. There is a development kit for cardlets. Not sure how open it is in terms of open source, but at least it's available without charge. And I never used the full development kit. I only used the command line tools, like in the Hello World example of that is published by ShadyTel. or some other smaller bits and pieces that I've played with on Java cards. So, and in those, just basically use the command line compiler and the converter for the cap files and so on. Then we have applications on the cards. Just excuse me for a second. So, as I mentioned, applications typically consist of executable code and file system. The executable code means you can implement commands which are invoked by the phone or modem in the case of SIM cards later on. But also commands that are wrapped or nested in this, which the phone receives via over-the-air channels from the operator. So you can implement commands for both of those cases. And in addition to that, you have a file system, which again has the structure, the content, the access control associated with it in this application. Now, what kind of card applications do we have on a SIM card? Typically, it's a combination of some of these today. So we have the classic 2G SIM application that was used for 2G networks and still exists on most cards for backwards compatibility. Then we have the USIM application for 3G and beyond. We have the iSIM for IMS. It's not mandatory, so you can do IMS or VoLTE without that one, but still it is present on some cards. And then we have applications for over-the-air remote application management and remote file management, sometimes even multiple instances of those applications, because remote file management could be separate for the master file and for the application dedicated files of these two. So in many cases, you have 3 OTA RFM applications on the card, each associated to some application. And then this RRM, the application I just mentioned briefly ahead of the talk, which is required for Android UICC carrier privileges following the global platform secure element specification. So all of these we need to install somehow on the card together with other bits, which then forms the SIM profile. So if the card is flash-based and the operating system is not already installed, then the operating system is like the first step to be installed. Then we install these applications that we need on the card. Those applications could either be native code or Java. Native code means native to the operating system in some close to machine binary format. Or it could be Java card applications that run inside this strange Java card virtual machine. So then, of course, the file system, and also important to understand, there are bits that are not part of the file system, which is the pins, for example, the PUCs for the unblocking pins, the administrative pin, and all the key materials. So a specific card operating system may decide to store those in files of the file system, but the specs don't mandate or specify that this information is stored in the file system. It could be in some other location of the card, some other form of memory that is not accessible through the file system. So that's why I consider this non-file system data, because the specs doesn't say it's part of the file system. So it is an implementation detail where those are stored, but of course they need to be put on the card as well as part of the profile. So how do you create such a SIM card profile? There are vendor-specific proprietary tools, typically with some graphical user interface to in an Explorer style view, where you can create the individual files of your file system hierarchy and specify the content and the structure and the permissions and so on. Those tools then store this in vendor-specific proprietary file format that you can, again, later load in this tool or edit and then create new versions of the profile. And at some point from this tool, you generate what's called APDU scripts. So APDU is the command, the application protocol data unit is the way the kind of messages that SIM card communication uses, and you create scripts for personalization from that. And these scripts are basically a concatenation of hundreds or thousands of commands, like create file for each of those files that you want to have on your card, update file or update binary for the content of each of those files if you have specified any. Then install commands for installing applications according to the syntax defined in the global platform specification. Yeah, and if you don't use this approach with the vendor-specific proprietary tools, of course, there's nothing that prevents you from creating those scripts either from hand or for some other custom tools. I mean, I have some, believe it or not, C code with APIs where I can basically call C functions, which then render these APDU scripts for creating files on cards. That's how I do at least some of my work when creating SIM card profiles. There's many different ways. In the end, you will have this script of all the commands that are to be executed as part of the profile, the personalization process. Now, of course, all of this vendor-specific stuff is not so nice in terms of portability, interoperability, and so on. There was one approach quite some time ago already by SIM-PML, the SIM Profile Markup Language, which is an XML-based format representing all of this profile content. I don't think it ever took off a lot in the industry, at least as far as I can tell. What is more used these days is the SIM Alliance interoperable profile format, which is an ASN1 based file format, because this is what is used in the eSIM universe, where you, of course, need a standardized interoperable format specifying these SIM card profiles, because the eSIM, the logical SIM that one operator provisions into an EUICC, the actual chip, of course, is nothing else but this profile. So when you install an eSIM on your EUICC in the phone or modem, then you're actually downloading such a profile. And since the chip vendor of your chip inside the phone can be any vendor, and the operator you install the eSIM profile can be any other vendor, there needs to be interoperability. This is not possible with vendor-specific file formats. So that's a new development. And one of the things I'm actually hoping for is finding time, as already a feature request ticket, to add this into PySim shell, so we can basically create SIM cards from this interoperable profile. So you could also take a profile in this format and deploy it on a SIM card using Osmo PySim, but that's future. Doesn't exist yet, this code. So how does this look like? For example, this is just a small snippet. I'm going to decrease the size a bit so it fits on the screen. Yeah, this is a small snippet describing interestingly, this is from some China Unicom SIM or eSIM that somebody has checked into a GitHub repository. Not sure why or how, but it's one of the few like supposedly real-world eSIM profile examples you can find out there. So this is the description of the pin 1 and pin 2 and the ADM pin of the card. You can see here unblocking pin reference. So with this PUC Apple 1, you can unblock the pin Apple 1. And it is apparently 1, 2, 3, 4 in ASCII if you decode this mentally. And here, likewise, it's 65502032. And if we and the ADM pin here at the bottom is slightly more elaborate. Or if we look at the next slide, I thought I had, it's on the same slide at the bottom. Also, this is how a file looks like described in this interoperable profile. So we see the file descriptor, we see the file ID, this 6F07. Those who have worked with SIM cards know this is the SIM, and this is the IMSI on the SIM. The security attributes, the size is 9 bytes, the short file identifier, and here we have the encoded, excuse me, the encoded IMSI that is stored on this card as part of this file control parameter snippet here in this interoperable file format. And so if you want to put this on, even if you have such an interoperable profile format and you want to put this on a physical card, then you will need some kind of tool that reads this and produces the hundreds or thousands of concatenated commands that will install all the files and configure all those bits on your specific card. Yeah, so now that we have a profile and the physical card, we need to bring those two together. And that is the actual personalization process. So in short, this means whatever is required to deploy the software and the configuration that defines the profile on the card. The details depend on the specific chip used. So as I mentioned before, some chips could have the entire operating system in mass-ROM or already pre-installed in Flash or something like that, or they have just a bootloader. So if no operating system is present, the operating system first needs to be installed via the bootloader, and those protocols and commands are highly chip and vendor specific. Sometimes also modules or even chip dies are pre-programmed with some probes already during an earlier stage of production to accelerate the personalization process. But I think the normal process is what I describe here, that all of this happens after the full card has been physically produced. The personalization process itself is often split in two steps. So we first have this shared and common personalization, which is basically all the stuff that's identical between all of the cards in a batch you produce. So if you produce, let's say, whatever, 50,000 cards or 100,000, then all of them have exactly the same shared or common personalization steps. That means same OS, same application, same file system structure, same content of most of the files. And then we have the so-called card individual dynamic data phase, where those bits that are individual for each of those SIMs, like the IMSI, the PIN, the PUC, the access control classes, the key materials, and so on, those are then deployed differently on each of those cards that are being produced. The actual script file formats I mentioned several times. These are lengthy scripts of APDUs. The actual format, I'm not aware of any common standard of those formats. Every factory seems to have their own custom format to execute those scripts, but they're extremely simple because, well, basically you only have 3 different things that can happen in such a script. You can reset the card, which is required quite a number of times. You know, if you install the OS, you reset the card to boot it and so on. Then you send some command and expect a possibly partially wildcard status word. So you say, well, create this file, and I expect a positive status word, and a positive status word in this command is supposedly whatever, a 9000 or something like that. And then for the dynamic data phase, there's some kind of template syntax for substitution of those fields that are dynamic, like ICCID, IMSI, MSI, SDN, PIN numbers, and so on. So those get then substituted into the script at production time. I have a couple of patches in my pipeline to add support for 2 of those script formats to PySim. So the LDR and the IPR format, but yeah, they're super simple, really. And whatever other factory might be using, it's again, in the end, it boils down to this. So it's just how to express those simple commands and expected responses in some kind of text format. So the common personalization is the bulk of the work. 99% or so of the card personalization is common, is identical for all of the cards, and it can take quite some time because, of course, each of those create file operations, which is the bulk of it, need to be, well, not atomic necessarily, but some kind of transaction. So if you create a file and then you unpower the card after it has acknowledged this, everything needs to be committed to the file system. So if you create hundreds or even thousands of files, then of course that's a lot of like committed transactions to the card, which take a lot of time. The UART itself also is relatively small, and card production time, of course, means cost. The longer it takes for each card to personalize, the more expensive is it going to be. So some card operating systems support the concept of an image. So you can basically take an image of one card once you've created your golden master, And that image then is sort of a like compressed binary single blob that contains all of the entire file system and everything, and that you can install much quicker since it requires much less communication on the UART, and it's only one transaction to the flash memory on the card. But that's a non-standard mechanism that just some operating systems support to accelerate this process. And this is followed by the dynamic data phase, where you have this script with templates, as I mentioned before. And after all of this has happened, we are at the end. Well, not exactly yet. What we still need to do is the so-called changing the card lifecycle state from what it used to be, which is personalization during all this time, to the so-called secured lifecycle state. And that's a one-way change in the card functionality that cannot be reversed. And at this point, all the security mechanisms become effective. So initially, when you program the operating system and you are in this personalization state, anyone with physical access to the card can read and write and configure and control every bit of the card. But after you've installed this profile by means of the personalization and you did the dynamic data, you specified permissions for all of those files, and the majority of the files maybe cannot even be updated by the user, by the normal user. And some data, like the secret keys, of course, cannot be read by anyone according to the permissions that go along with them. And all of these security mechanisms now become effective when you do the transition into the secured lifecycle state. And from that point onward, it basically is the SIM card as it is received by the end user, or first by the operator from the factory, but then also by the end user who uses that SIM card, and it behaves with all the security bits in place. At the same time, during the dynamic data phase, also there happens often laser engraving. So that means the some of the dynamic data parameters, most likely the ICCID and the PIN and PUC values, are being laser engraved on the plastic card, while the personalization of this data into the chip is happening. And then finally, we have that card, and it can be shipped to the end user. So that's the process, and we can come to questions. Thanks. So there is a question. Some SIM interposers have SDK menus to change IMSIs. Would that work on Sysmocom SIM cards too, or would it be prevented by the replication permissions between applets? Well, an interposer is between the card, and it's basically a man-in-the-middle attack against the SIM card. And no matter what you do as the SIM card manufacturer, you cannot defend yourself against it, because the protocol between SIM card and a phone is not authenticated or integrity protected or anything, and you cannot change that. You would have to change the specs so the phones implement something like that, and you would have to change the SIM cards. So no system. Yeah.
What I actually mean is, could you create an applet that changes the data stored on the USIM file system? Like, could you have an applet on the Sysmocom SIM cards that is able to change the file system contents?
Yeah, of course. There's even an example published for this. It's on git-osmocom.org. It's in the pseudonymization project. So in there we have the SIM applet, the IMSI pseudo SIM applet, which basically uses over-the-air messaging to change the IMSI on the card.
Yeah, thanks.
Welcome. Their FOSS implementation of the Java cards VM, I'm not, well, actually, that's not entirely true. I think I've seen something, but I never looked at it. I didn't never do much Java card work. There is a list of a curated list of Java card applications, and I think this also has, I think, 1 or 2 open source emulators, basically. I mean, not an implementation that you can put in an actual card, but at least an emulator in which you can run Java card applets and talk to them. So what do we have? Java card simulators and emulators. Yeah, yes, you can find some, even apparently some implemented in Node.js. If you want to have a Java virtual machine implemented in Node.js, some people might find that exciting.